All right, so in this video, we're going to be looking at what if it's a graph, but specifically we're going to be looking at integrals. This typically involves one of two things. If they give you a graph and it involves an integral, it's either because they're doing area volume or they're asking you for an integral defined function of some sort, okay? And we'll get into those as we go through the video. But one of the ways you can tell when you're looking on the AP exam that it's more likely to be an integral, an area volume graph, is that these are not typically precise. There's not typically a grid behind them. They are more just generic functions. That way they know that you can analyze, or you don't have to analyze or calculate as precise. So if you see a graph that is just defined, like here's a graph right here, A, B, C, it's not really defined well. Here's another graph, not really defined well. There's no points, there's no grid. Here's another one. Again, not every point is really easy to tell. So when you see that situation, you're typically looking more at a graph that's going to involve an integral, an antiderivative, okay? So let's get straight to it, and let's talk about area volume first, because that's one of those comments or those topics that students tend to mess up more than they should, okay? Let's just start off with this figure, and let's let the region R be defined as that region inside these two functions. So to find the area of R, what we're going to do is we're going to take a piece of the function. Now, I typically think of this as just a random line segment, just a length of some sort. And this length will change. Over here, it's fairly big. As you get closer to the ends, it gets smaller, right? But all you have to do is draw it at a random point and then think about how that value would be calculated. And I know it sounds crazy, but let's just talk real quick. If you have a height of 7 and another height of 5, how do you find the distance in between them? You literally subtract. So if you have a value, now these are y values, right? G has a y value and F has a y value. They are changing in terms of x, but that means the difference in their y values would represent that length. So all we're going to do, this length is G minus F. And to find area, then all we're going to do is we're going to take that length and add them up, accumulate them throughout that region. Now remember, they are defined in terms of x. Every one of these is defined in terms of x. So when I think about this, I'm going to take that length and I'm going to add them up, which is the integral, the accumulation, okay, the sum, if you will. And I'm going to add them up from the smallest x value to the biggest. Well, there's your smallest from A to the biggest, which is C. That would be at A, that would be at C. And you add up all those lines with respect to x. So the area is a pretty easy thing to do. Then on the AP exam, they'll sometimes ask you to create cross-sectional area or cross-sectional volume. All that simply means is now we're going to take this line segment and create new figures. And as a side note, let's just think geometry here. If I take a line and I use that line to create a square, well, if this is something, then isn't the area of that square something squared? And without going through all the proof, because you've done this probably in class, if this was a equilateral triangle, that area happens to be the square root of 3/4 times this length squared. If it happens to be a semicircle, then that area happens to be pi/8 of something squared. And if it happens to be that it is a right triangle that's isosceles, then it is the square root of 2/2 times, or I'm sorry, it's 1/2 of something squared. Try to make that one harder than it is. And what we notice is that it doesn't matter what cross-sectional area we're creating here, they are all some version of the square. This one is, in a sense, we just took away part of the square. This one, we took away part of the square. This one, we took away, this one's easy because we took away exactly half of the square. So that's why every one of these constants is going to be less than 1, because we're always on these cross-sectional areas. If we use that length to create a new figure, a typical figure, then it's going to be basically chipping away at the square. It's like chiseling away to create that new figure. Now, I'll show you some examples where there are times where it's not that case. They have said on the exam before, what if your cross section creates a rectangle and this happens to be 7 times longer? Well, it's not harder, right? It means that this is going to be 7 of those squares, this area. So the reason I say that is if they ask for a cross-sectional area, then all we're really doing is taking this length and turning it into area itself to create volume. So for instance, if I were to take this and make it a cross-sectional square, this square would have an area of that square would be G minus F squared. Okay? So if they want to know the volume of, they typically say this as a cross section consisting of squares that are perpendicular to the x-axis. And that's really just to identify the cross section means that we're going to take the areas and create volume. And then we have squares perpendicular to x, just tells me they are vertical squares. So how are we going to find volume? Well, we're going to just simply take those areas and add them up over those x values. So there's 2 easy questions to do. And then the other thing they'll sometimes ask that they ask more than often, is they'll ask you to do revolutions. Now, what I do is I think about, if you take a segment and you start revolving it across an axis, then it creates a circle. If you revolve it around an axis, it creates a circle. But if this length is G minus F, then when you revolve it and create a circle, it's really representing the radius of a circle. So when you revolve it around, the area that's created is pi r squared. So just like the square area, the circle area is a little different. But if I want to make that into volume, I simply add those up. And we're done. Now, that'd be nice if they were that easy on the AP exam. But typically what they do on these questions is they take that radius and they don't revolve it here, but they revolve it across a different axis. Well, we still get a circle, right? We're still going to get a circle. But now we're going to get a solid circle. And I'll identify that we have this region is solid because it's where the line segment came from. That's solid, but everything inside is empty. And so now when we revolve, it creates what we call a washer. So now what we have to do is a little different than what we've done so far. Most of the time, you're just taking that length and adding it up or making it into volume. Now what we have to do is consider that when you have a circle, let's say we have a circle inside a circle, and this radius is 2, and the big radius is 5. Well, how do you find this area inside? You would do pi times 5 squared and get rid of pi times 2 squared. So you take the entire circle, the big circle, that looks confusing, big circle, minus the little circle. And that's how I approach these questions. So back to the calculus here, the circle I created here, the big circle is actually going to be from this point to this axis. We call it an axis of revolution. So the big radius is going to be the top function. We'll just say it's G. So we'll say it's G minus the axis. That would represent this length. And if you narrow everything down and think of it in terms of length, these problems get a lot easier to do. And then we have an inside radius, and we're going to assume that this function was f. So this inside radius would be f minus the axis. So that means if I do pi times the big radius squared, that's the big circle because that's the entire radius, minus pi times f minus the axis squared, that would represent just the area of the outside of the outside of that small circle, the washer, if you will. So if we add those up from, let's say, A to C, then we're done. So that's how we're going to think of all these area volume questions in terms of what's the length. Is it a length or does it become a radius of a circle? So let's jump straight into it and let's look at one of these. Whoops. All right. Let's look at this first one. Okay. So we have a graph. You notice it's not well defined. We don't know a lot of the points. And they want to know the area of the shaded region in the figure above. So I'm going to break this down as a length. Okay. And that length is going to be f on top. The f function is on top. And the g function is on bottom. So that would be the measure of that length for any given x. That's the y values for any x, okay? So how do we find the area? The area would be adding up those lengths from the smallest x value. It's in terms of x. This is what tells me it's in terms of x, okay? And so it's going to be the smallest x value, which is A, to the biggest x value, which is C. Okay? And so this is a pretty basic one. We're just taking those lengths and adding them up. Okay? For instance, here's another one. What represents the area? So let's look at a length. Okay, what represents the top y value? Well, it's always D minus the bottom y values are represented by F. And then we're going to find the area by adding those up from the smallest x to the biggest x, which is from A to B, and we're done. Now, sometimes those we hope to get on the exam, not really any calculation. You're just trying to see how to actually find it. Well, sometimes they're not so nice. Take this one, for instance. The figure above shows a graph. We have two different graphs, and they want to know the area. I still know that I have a length. Okay. But now they didn't label which function was which. So it's my job to determine which one of these is that function and which one of these is this one. And by process of elimination, it's a lot easier to tell where y equals 2x is. That's the line. Okay? So if that function is the line, then that means the other function is the curved function. Okay? So if I'm finding that length is 5x minus x squared minus the other length, the y values to the other length is given by 2x. So to find this area, we're going to take those lengths. Whoops, 5x minus x squared. And we're going to add them up from the smallest x value, which is 0, to the biggest. Oh, no. They didn't tell me what the biggest x value is. But I know that that's a value where these two meet. That means that the y values are the same right here. They intersect. So I'm going to have to now take these two functions, set them equal to each other, and let's move the x squared over to this side by adding it. Let's subtract 5x from 2x. Factor out an x. And I get that x is 0 and 3, where these two functions will meet, where their y values will be the same. That's what we did here, right? Well, I already knew 0. So what this tells me is I must be looking at 3 as the other x value. Don't forget your dx, okay? So this question really comes down to now analyzing and doing that antiderivative. This we did on another video, how to do the antiderivatives. Quick and easy to calculate, and then you can do the algebra to finish it off. Okay? All right, but let's get into a little meatier problem here on the open response. Love this question. Kind of a tricky one. So we have a region R. Now, let me give you a quick little hint. If you ever see a shaded region R, it's area volume. It is area volume all day long. Somewhere they're asking area volume, okay? So let's go straight to it, and let's look at the first question. Well, yeah, let's do that. All right. So R is this region enclosed by two graphs. So we have a graph G, and then we have a graph H. Oh, man, they didn't give me either one of them. Man. Well, let's see. How do I figure out which of these is which? Well, I know that a quadratic that has a negative leading coefficient has that U shape, that downward U shape. So that's got to be this guy, right? This has to be H. Okay? Which means that the bottom function has got to be G. You may have figured that one out by knowing that cosine will start at 1. That's another way. But they're asking for a little bit of algebra there. And so now we get into part A. Find the area of R. So let's take one of these lines. Okay. And my question is, what is the length of that line? Well, it's going to be the top y value minus the bottom y value. So to find the area, we're going to take H minus G. We're going to add those up from the smallest x value, which is over here at, well, actually at 0, to the biggest x value, which looks to be at 2. And on the exam, that's only going to be part of the way, because now, notice they said, find the area. So now they're shifting into a question that we did on another video, which is actually wanting you to do the antiderivative. H is 6 minus 2x minus 1 squared minus g is this negative 2 plus 3 cosine pi halves x. And so they're wanting you to actually calculate this. Now, we did a whole nother video on that, on how to do antiderivatives, but just as a quick reminder, we'll review this real quick. So let's first of all, I don't like so many brackets. I'm going to knock down this bracket here by distributing that negative sign. That's going to make the first one a plus 2, then a minus 3. And I'm showing you this for one reason. First of all, my students are great at writing the formulas, not so great at actually finishing the area out, okay? You have to actually finish it out. So now, we're going to take his antiderivative, which is 6x, okay? Then we have a minus 2, which is a coefficient. That stays by itself. And then we have a function outside, which is squared. So we have the function cubed over 3 by the anti-power rule. Okay. Leave the inside alone. Divide by that derivative, which is 1. Then we have a 2, so that's 2x. Then we have a coefficient out in front. Leave that alone. Now, what function has a derivative of cosine? That would be sine. But that happens to be a function outside because of the parentheses. So I'm going to put that pi halves x inside and divide by that derivative. So there's the antiderivative, and I'm going to evaluate that from 0 to 2. And literally, I'm just going to replace all these with 2 and subtract every one of these evaluated at 0. And I'm not going to simplify anything after that point. If that procedure looked a little tricky for you, check out the video we did on taking antiderivatives, okay? So part A, back to the area volume here. Part A, not hard to figure out the formula, definitely a more serious question on how you calculate, okay? So now let's look at part B. Region R is the base of the solid. For the solid at each x perpendicular to the x-axis, so we're talking about at each one of these lengths, right? The cross section perpendicular to x just means the length, okay? The length happens to have an area of 1 over x plus 3. Well, now wait a second. If we already know the area, then isn't the volume taking that area and just adding it up from the smallest to the biggest x? So from 0 to 2. And that's it. That's literally all you have to do. Now, you may be saying, well, why didn't we have to create some area with like what we did earlier? I've lost my paper here. You know, earlier we talked about making these into different figures, right? Why didn't we have to use one of these formulas? Because every one of these formulas was trying to get the area. They gave you the area, okay? So again, this is not all the points because you have to find it. I'm not going to go through that right now, but you could then solve, okay? A lot easier than the one we did in part A, and you'd be done. Let's look at part C. Write but do not evaluate an integral that gives the volume of the solid when R is rotated about y equals 6. All right, now let's think about this. Where is y equals 6? Let's see. I got 1, 2, 3, 4, 5, 6. So somewhere up, wait, 1, 2, 3, 4, 5, 6. Yeah, somewhere up here, right? Draw that better. Okay? So that's going to be my y equals 6. Well, that kind of changes my lengths a little bit, right? In fact, do you notice if you go from that revolution, that axis, all the way to the end of the region, that there is a gap. There's a little gap there. So that tells me that when I start revolving this around and getting my circle, that I have a big circle and then an inner circle, a little circle. So let's start with the big circle. And by the way, the reason you know it's the big circle is because it's from the axis to the end of the region. Because when it revolves around, that's going to be the big circle. So that length is going to be this value, the y value up here is 6, minus these y values are g. Okay? So that's that big length. Then you notice that we've got this little length right here. It's hard to see. This little length here from here to here. Let me do orange on that. That didn't help at all. So what is that length going to be? Well, the y values on the top are 6, and on the bottom they are this function which we said was h. Okay? So this is going to create the big circle. This is going to create the little inside circle. So how do we now make this into volume? To do the volume, we're going to take the big radius, 6, minus g, and we're going to make it into a circle, pi r squared, minus, we're going to take that little radius and do pi r squared. And we're going to add those up from the smallest x to the biggest x, noting that x's are variable. And on this question, you'll notice, I love these on the AP exam because lo and behold, guess what? It says, write but do not evaluate. All you have to do is just write it. So anytime you're given an area volume question, break it down into lengths and then ask yourself what those lengths are doing. Are they being added up to create area? Are they being changed into some area that we're adding up to create volume? Or are they being spun around where now these lengths are becoming the radius of a circle? And the area volume questions, if you practice that, they get a lot easier. So I want to take a side note because that tends to come up on the exam a lot. But they will sometimes give you a graph and they will ask you to do something with an integral, and it may not be so obvious that's what they're looking for. So first of all, I'm pretty sure this is not going to be area volume because I don't see an R. I don't see a region that's shaded. I also have very exact values, okay? I wanted to mention this question because this is coming up more and more frequently working with these integral defined functions on the AP exam. And what they do is they give you a graph. Now notice this is G. And it just so happens that G is the derivative of F. So G is also F prime. Okay. And then they ask you this question where they give you a point and ask you for another value. Okay. And again, this has come up so frequently on the AP exam that it's almost to the point where if I see a graph and I see a value like that, I know we're going to be doing this type of question with an integral defined function. So let's pause for a second before we get to it, and let's remind ourselves of the first fundamental theorem of calculus. The first fundamental theorem of calculus says that if you do the antiderivative of the derivative function from a to b, it is f of b minus f of a. So with a very small bit of algebra, we can change this around. I'm going to add f of a to both sides. And I notice that now f of b is actually the same as f of a plus the integral from a to b of f prime. So now I have a function that is an integral defined function, okay? And the way I remember this is that essentially this is the final value, f of b, because notice b is at the end of the interval, is the initial value plus the change in the value. And this formula, we didn't probably use it as much about 5-10 years ago, but now it's come up so frequently on the AP exam, you probably should just memorize this formula, that the final value of any function can be given by the initial value plus this change in the value, okay? And keep in mind, the change, I should probably add to this that it is the total change, because the total is from the antiderivative, the accumulation, and the change is because we're adding up the changes, okay? So the reason I do that is if you focus the final value of any function, doesn't matter what it is, it could be velocity, acceleration, whatever. The final value is always the initial value plus the total change, okay? So looking at this first question, if f of 1 is equal to 3, what is the value of f of negative 5? So f of negative 5, that's the final value. It's going to be the initial value. Now, the initial value, all we can really base it on is a value that they give us. And they gave us f of 1. So I'm going to say it's f of 1 plus the total change over that interval. So it's going to be the total antiderivative, accumulate the change, total change over that interval. Well, remember, it's from the initial to the final. So it's from 1 to negative 5. Okay? And I know that's backwards. I don't care. Okay? It's from the initial value to the final value. So now this problem comes into just calculation at this point. We know that f of 1 is 3. And I don't know how to do f prime when all I have is g. Oh, wait a second. F prime is g. So this, I can make a substitution, and I can call it g, or this function. And so from this point, I've picked up most of the points on the AP exam, let me point out. From here on, I'm just picking up maybe a point or two extra. Probably just 1 point at this point. But if you keep in mind, it is the same idea. If they give you a function and they ask you and they give you a value and they want another value, you're always going to go back to the final value is the initial plus the total change, okay? From here, we could evaluate this. You got to do an antiderivative. We did in a different video. So I'm not going to go through that here. But let's just look at one more example, okay? Here's another example. So in this one, the big red flag that I get is they gave me a value. If they gave me a y value, a point on the function, and a graph, that change formula is going to come into play, that integral defined function, okay? So let's start with f of -6. If I'm finding the final value of the function, the final value is the initial value. Well, the only one they gave us is this. So it's f of -2 plus the total, and I always say it as I'm writing it, the total, the accumulation, change, the derivative, total change from, in terms of x, from initial to final. So from -2 to -6. Okay? And in this question, you have to take another direction. You have to know how you get f prime. Oh, I'm sorry, they gave us f prime, right? So there's no reason to rewrite it. So we have a graph of f prime. Now I need to know if I'm given a graph and I want to find the antiderivative, that relates to area. So let's see, on the graph, this would represent the area from -2 to -6. Okay? Which, lucky for us, it's just a triangle. Area of a triangle is half of the base, which looks to be 1, 2, 3, 4, times the height, which is 1, 2. So that area is the area of a triangle. But notice we're going from -2 back to -6. And when you go backwards, the change in those x's are negative. So that makes this orange value, that makes it the opposite of that area. Okay? So that's the orange area. And so to find this one, f of -2 was 7 plus this area was the opposite of that triangle area. Okay? Keep in mind that there are two things that can make an area with an integral negative. It's either the x's are negative because we're going backwards, or the y values are negative because we're below the x-axis. So that's all you have to do on that one. So typically, if they give you a graph on the AP exam, it's going to be one of those area volume questions where you have to figure out those lengths, or it's going to be one of these where they give you a point and you have to find another value.